Chris is doing a fantastic job in his role as novice chairperson here in 2023. Many of you know Chris. If you don't, he is the current novice chairperson. He's also an active member of the North Houston Astronomy Club and the Fort Bend Astronomy Club. He's a member of the University of Texas Astronomy Department Board of Visitors and is a regular volunteer at the George Observatory. And tonight, Chris is going to be sharing with us his presentation, which is about putting your observing in context. So Chris, go ahead and take it away.
Thank you, Joe. Let me, oops. All right, what did I do?
I stopped the share, so I'm not sure.
All right, there we go. Okay, never mind. Okay, here we go.
And as Chris is bringing that up, if you have questions for Chris during this talk, please feel free to use the chat feature that we have in Zoom here. Go ahead and ask your questions there, and we'll get to them at the end of the presentation. And I already see Bobby Taylor says she forgot to get the cloud filter. Yeah, we all did on that one.
Okay, can you see my screen in full?
We can, Chris, yes.
All right, great. Well, good evening, everyone. Thanks for the introduction, Joe. Very much appreciate it. So tonight, it's going to be a bit of an ambitious presentation, putting your observing in context, a brief survey of the universe. I've been involved in astronomy for about 3 years, done a lot of self-study, taken some courses, and this presentation tonight brings together a lot of information and knowledge that I've accumulated over the last 3 years. But like I said, it's pretty for me, it's a pretty aggressive topic, and I hope to do it well because I think there's a lot of good information here for the novice. So when we first start out in astronomy, we spend a lot of time, learning how to find objects, and then once we find objects, be it a star cluster or a nebula, I spend a fair amount of time just admiring the beauty of the object. But inevitably what happens is you begin to ask questions such as, what am I looking at? How did that object get there? And one that bothered me for a long time is, where is this object with respect to us and everything else? So the objective for tonight is to try to answer these three questions. I'm going to be talking about processes and structures. We'll cover processes that create many of the objects that we see out in the cosmos. And then also talk about structures in the second half of the presentation to tackle some of the larger objects such as galaxies and groups and clusters, the things that galaxies tend to come together and create. This presentation is going to be probably a mile wide and an inch deep. So at the end, I'll leave you with some resources that you can pursue in order to learn more on your own. And believe me, I'm still learning. So it's an ongoing process. Before we get into a discussion on processes, I want to cover a couple of things first. First, some important principles. Gravity plays a big role in how our cosmos is created. Gravity is that force of nature that keeps our feet firmly planted on the earth. And more generally, gravity is an attractive force that will bring together two objects of mass. Fusion, in particular hydrogen fusion, is a big principle and something that you'll need to understand in order to understand what's going on out there. If you take a couple of hydrogen atoms and you apply enough pressure, you can get those two atoms to fuse into a helium atom, and in the process release a tremendous amount of energy. There's a small amount of mass that's lost in that fusion reaction. And if you remember Einstein's equation, E equals mc squared, E being energy, m being mass, and c being the square of the speed of light, you can tell that a small amount of mass can generate a large amount of energy. The gravity and fusion play a big role in creating the heavens. The last principle here I want to talk about is angular motion. In general, angular motion is very prevalent throughout the cosmos. Our Earth spins, we orbit around the sun, our solar system orbits around the galaxy, the galaxies can rotate. So angular motion is a very prevalent feature in our cosmos. And if you think about it, once something starts spinning, there's really nothing out there to stop it. The other thing about angular motion I want to just touch on briefly here is our figure skater over here to the right. If you've ever watched a figure skater in action and you've seen her begin to spin, you'll notice when her arms are wide out, she'll be spinning very slowly. But if she brings her arms in closer to her body, the volume of the mass that she occupies decreases. And when that occurs, she spins faster, called conservation of angular momentum. But that's a feature that we'll come back to here when we talk about planetary creation. So keep that figure skater in mind as we get into our discussion. The second thing I want to just touch on briefly here before we get into processes is the Big Bang, and in particular, where all the hydrogen comes from, the fuel that is used to create the cosmos. Where did that come from? There's a lot of complicated study and a lot of complicated theories and explanations around how hydrogen get there. The extent of my discussion is going to be that sometime in this area here, before the first stars were born, that's when the hydrogen from the Big Bang was created, and that's what we're still using today in order to create stars and other objects in the cosmos. So I'm going to leave it at that. So let's get into processes, and the process that we're going to really focus on here first is the life cycle of a star. And you see a very simplified diagram here that takes you from a nebular cloud through star creation, creation of a supernova and a planetary nebula, and then recycle of that material back into the cosmos. So we're gonna walk through this step by step. And the first area of the process we want to talk about is a stellar cloud with protostars. So the first example of a stellar cloud that I wanted to show up here was the Orion Nebula. And we talked about the Orion Nebula last month. It's the closest region of massive star formation to Earth. It's only about 1,400 light years away. And this particular cloud has it's predominantly hydrogen, and it has the right conditions that promote the creation of stars. There are density differences. There are cold temperature out there. The conditions in this particular part of in this particular nebula, in this cloud, again, are conducive to star formation. There are currently about 700 stars in various stages of formation, and many of these stars, I believe, are protostars. Tried to get a reconciliation of the number of protostars versus the total number of stars in the various stages of formation, but there are suffice it to say there are a number of protostars in the Orion Nebula. So what is a protostar? Well, a protostar is a young star that's gathering mass from the stellar cloud or the nebula, and gravitational collapse forms an internal core. So because of the nature, in our case, of Orion, the gas has a tendency to collapse and form, again, due to gravity, a core of material. And in this case, it'd be predominantly hydrogen. There's also a thing called a protoplanetary disk that can form around it can form an orbit around the core. Orion has somewhere around 150 plus protoplanetary disks that have been observed. And we'll come back to protoplanetary disks when we talk about planet formation. But just that's what a protostar is, and the beginning of life for a star. So the next step in the process is really full-fledged steady state star formation. And you see here there's a couple of different kinds of stars that we're referring to. There's a small star and a large star. Now that's kind of a gross exaggeration, but think of it this way. Small star being stars roughly the same size as our own sun, and larger stars being, many times greater, anywhere from, 5 to 10 times greater than the size of our own sun. So at some point, you're going to have enough pressure developing in the core of these protostars for fusion of hydrogen atoms to begin. And again, like I mentioned earlier, the hydrogen atoms are going to come together and form helium. And because you're losing mass when you have that reaction take place, this missing matter is converted into energy. And that's really the fuel that we have out here to power the stars, have them give off light and heat. Here is a picture showing a star in equilibrium. So protostar is in the process of being born. This is really what you get when it's out of the womb and it's operating and running around all on its own. And you have a fabulous feature of nature happening here. You have this inward pressure of gravity, which is shown with these green arrows, pushing out against this pressure from the fusion reactions that are occurring in the star. And this is a self-correcting, very stable situation, and because the two forces balance each other out. And this star that is in this this configuration can last many years and heat planets in its solar system and just be a very stable member of our intergalactic neighborhood. This diagram here is called the Hertzsprung-Russell diagram, and you'll see. And I'll point out the main sequence stars, but I do want to spend some time going over this diagram because it's a really nice one-page reference for finding out a lot about various stars in the universe. So I have here circled a group of stars in what's called the main sequence. And the main sequence is essentially a star that's in equilibrium. It's happy, the forces are balanced, everything's wonderful. But a little bit about this diagram, because we'll come back to it a couple of times further in the presentation. The surface temperature of the star is down here on the x-axis, going from decrease or low to high temperature left to right. The y-axis here shows the brightness of a star in terms of solar units, or in relation to our own sun. And you'll also see some crosshatches out here that show you what the size of the star is relative to our own sun. And this is in solar radius. There are other crosshatches here, well, really demarcations here that show you the mass of a star relative to our own sun. So up here, Vega is roughly 3 times the size of the mass of our own sun. Spica, 10 times the mass, so on and so forth. And then you'll also see some demarcations here that show you the expected lifetime or lifespan of a star. So our own star has roughly a 10 billion year lifespan. Further up the chain here, if you go to up close to a star like Spica, you're only looking at about a 10 million year lifespan, which is relatively short. Intuitively, you'd think that a larger star having more hydrogen would last longer, but the rate of fuel consumption is so high they don't last as long. Again, very handy chart, and we're focusing in on here that main sequence for stars. When they're operating and they're happy, and everybody in the solar system's happy as well. Here's a great example of a star on the main sequence. And let me just back up 1 second. Here is Sirius right here. And here is a lovely image of Sirius. This star is located about 8.6 light years away in Canis Major. So it is a star that's out in the winter sky. And if you're out on a clear night, and obviously not tonight, but on a clear night, you just can't miss this thing. It's the brightest star in our sky. It has a diameter roughly 1.9 times the diameter of our own sun, and it's a double star. It's interesting. It has a companion star, Sirius B, which is a white dwarf, and down the road that could cause some real fireworks. And I'll talk a little bit more about that when we talk about stars near the end of their life. But Sirius A, which is the main star, and Sirius B could really get into a cosmic tangle and really cause some fireworks. Just like dogs, when they have puppies, they don't typically have one puppy, they have a whole litter. And in this similar vein, stars can form in star clusters, in this case, open star clusters. Open star clusters, the stars in those star clusters come from a common stellar cloud. So Orion, if you think about it, having 700 stars in various stages of formation, you conceivably could have an open star cluster when those stars are finished forming and the nebula is blown away. Typically, an open star cluster will have anywhere between 10 and 1,000 stars. They're loosely bound by gravity. Over time, radiation will disperse the cloud of origin. And since these stars are of similar age and composition, clusters really provide a good laboratory to study the effects of mass on how stars develop. So if the age and the composition are the same, if the stars can form into different sizes, you can really begin to isolate that feature and see, what kind of effects you get from the mass of stars. So star clusters are something that I really hadn't appreciated much, but the more and more I look at these, the more and more I kind of dig them. Okay, so we just talked about stars that are on that main sequence. They're happy, we're happy, everybody's happy, but the party can't go on forever. When stars deplete their source of fuel, hydrogen, they begin to change configuration and change characteristics. And what you see here, again, back on the old HR diagram, are two groups of stars called giants and supergiants. And in particular, what's happening here for the giants, we'll talk about those since they are stars that are close in size to our own. When they run out of their fuel, what happens is the ash or the remaining material from all the hydrogen fusing is the helium, and that helium will be in the core of the star. It won't be hot enough to fuse itself. So gravity will begin to take over again. And when gravity does, because gravity can impart some really high pressures and raise the temperature of that core, you'll get ignition of hydrogen that was out in the outer shell of the star. And when that occurs, the star will actually expand in size. And it's this expansion that gives it the characteristic of being a giant. If you have stars up here that are in the neighborhood of 8 to 10 times the solar or the mass of our own star, these will be big enough that they can actually form supergiants. And again, this is just because there are larger stars, they'll have larger shells. This gas can ignite and expand. And that's what you're getting in this phase here. And it doesn't last as long as the main sequence, but it can go on for quite some time. This diagram here gives you a nice pictorial to kind of show you the relative sizes of these stars. So you'll see our own sun over here, main sequence star. It is a fraction of the size of Aldebaran, which is a red giant. And Aldebaran is a fraction of the size of Betelgeuse, which is a supergiant star, a red supergiant. So this gives you a nice picture of the size of these stars relative to one another. Over here on the far right, you'll see a white dwarf, which we haven't talked about yet in comparison to our own Earth, and roughly the same size. But looking back here on Betelgeuse, you can see that the orbit of Venus easily fits within the size of that star. So that's just to kind of give you a comparison of size between these stars. This picture right here shows a super. Let me go back and get my terminology. A red supergiant, excuse me, in its evolved state. So you can see down here, you've got iron that's in the core, and you have a number of reactions that have taken place over the course of its life to get you to that iron. So what I wanted to mention with this slide are a couple of things. One, these brackets that you see here, where I show it as small stars. What I'm trying to describe, or what I'm trying to communicate here, is that a star the size of our own sun will fuse hydrogen into helium, and then we'll go on to fuse helium into carbon and oxygen. But that's the end of the road for a small star like our own. For a larger star, stars that have anywhere from 8 to 10 times the mass of our sun, the fusion reactions can go on much farther. So carbon can actually fuse into neon and magnesium. Oxygen can fuse into silicon and sulfur, if I've got my chemistry right. And then these two elements can fuse into iron. Now, these reactions here are what are called exothermic. In other words, when you fuse these elements together, you'll actually give off energy. But when you get to the point where you've only got iron, that's the end of the road. Iron's what they call endothermic. So you actually have to put energy into iron in order to make it fuse any farther. And it's just not going to happen under its own volition with a star like that. So this is for a small star, this is kind of the end of the road here, carbon and oxygen. For a large star, iron is the end of the road. And when we reach the end of the road, you get some really spectacular things that can occur. For a small star, you get the creation of a planetary nebula and a white dwarf. For a large star, you get a supernova, which can result in either a neutron star or a black hole. And so we'll talk a little bit more about these. So I mentioned earlier about white dwarfs. So when our own sun will go up into this red giant phase up here for at some point down, the road after it gets out of the main sequence. When the fusion reactions in this phase of life cease, this star will actually collapse down to what they call a white dwarf, and it'll actually end up in this part of the HR diagram. And so this is a great example of a planetary nebula and a white dwarf, the ring nebula M57. When again these after the red giant phase, these stars will begin to shed or expel their outer layers of material, and that core of the star will collapse down into what they call a white dwarf. And that white dwarf is roughly the size of our own Earth. A white core is out of fuel. It's not fusing material or burning anymore, but it still is hot. And it's this heat and radiation coming off that white dwarf that provides the energy to ionize the gas that it had previously shed when it was in the red giant phase. And you get some very beautiful objects here. The ring nebula is one example, but there are other planetary nebulas. They have different shapes and colors depending on the circumstances around their demise. But it's this radiation from the white dwarf that's ionizing this material in the shell, and that's why they have their beautiful color. A neutron or a supernova resulting in a neutron star is what can happen to a large star. And here's an example that we talked about last month, the Crab Nebula. This nebula is actually a remnant of a supernova, and this resulted in the creation of a neutron star, the Crab Pulsar in this case. And if you remember from the discussion last month, this thing is spinning at about 30 times a second. It's emitting radio waves all the way up to gamma rays. It's very active. And here we've got some actual images of the of the neutron star itself in the nebula. Another possibility is the creation of a black hole. So black hole will occur when the final mass of a red giant star is 2 to 3 times the mass of our own sun. At that point, it's a candidate to become a black hole. And a black hole, in simple terms, is just a point of infinite mass and density. No light can escape beyond the event horizon. And if you fall in, it's kind of like the song Hotel California. You can check out anytime you want, but you can never leave. You're stuck if you survive the fall. So that's a black hole. And those are very spectacular items, and they serve a purpose. They actually recycle material that goes back into the interstellar medium, into clouds, nebula, etc., for further processing. And this is the material, the stuff that planets are made out of as well. So that material gets reprocessed back into the cosmos. And this is, again, another really handy one-page reference that I encourage you to study if you get some time. This is called the origin. It's a periodic table, but it shows you the origin of various solar system elements. So we talked about the Big Bang. And the way you would read this is the color coding here. So if an item has this blue, shade of blue, like hydrogen does, that means that material came from the Big Bang. If it had as a yellow designation, like here, that denotes that it came from a low mass, dying low mass star, like our white dwarf in the Ring Nebula. And then over here, if it's green, it has it emanated from an exploding massive star or a supernova. There are a couple of other items here on the chart that we didn't cover in any detail. I'll just mention them briefly tonight and leave further study to you folks on these. But you can get a lot of the heavier elements down here created from merging neutron stars. Now, whether that merger results in a super duper supernova or a gamma ray burst or something else of that nature, I really don't know. But merging neutron stars create these other elements, these heavier elements that you see down here. I talked about Sirius A and B, the Sirius with its companion star being a white dwarf. One thing that can occur in the life of a white dwarf with a companion star, if that companion star gets close enough by virtue of expanding during its red giant phase, the white dwarf can actually suck off material from that star. And if it gets big enough, it can explode like a supernova. And that's what you're seeing here with this lighter blue shade. These elements here on the periodic table are part of their the percentage of their creation came from exploding white stars. Again, not something that I studied a whole heck of a lot in preparation for this presentation, but something to be aware of. One other thing I'll just point out here, again, if you look at a particular block here, and you'll see that it has 2 colors in here, and these shades may occupy, different sizes in that box. That's just trying to give you a rough idea of the percentage of that element that came from, say, in the case of carbon, the percentage that came from dying low mass stars versus an exploding massive star. So a lot to digest with this this table, but well worth the effort to study and understand it. It took me quite a while to get there, and I probably have more to learn. Here is the Eagle Nebula. And what I wanted to do is show you a picture of a place in the cosmos that actually received some of this recycled material. So I did a little research on the Eagle Nebula, and I read a paper from the University of Pittsburgh, And some researchers there had studied the pillars of creation here, and it determined that there are microscopic dust particles in those pillars that contain graphite and certain minerals found on Earth. So to me, that was a real telltale sign that the Eagle Nebula has in fact been enriched by these previous stars that have lived their lives, died, and then recycled their materials back into the cosmos. So I thought that was kind of a fitting nebula to show here at the end of the process, besides it being a beautiful nebula. I want to just circle back real quick and talk about planet formation, and I'm going to do it in somewhat of a simplified manner, but I really thought it merited some discussion. So you'll see here that this small star with the solar system out here to the side. If you remember our figure skater, as that figure skater is collapsing her arms, she's spinning faster, but the skirt around her leotard is actually flying out and kind of creating a sombrero kind of look as she spins faster and faster. This is kind of the same. That's a decent metaphor for what happens when a protostar core is collapsing, and you have that protoplanetary disk forming. As the star is condensing and spinning, it tends to flatten out that protoplanetary disk. And I like to refer to the material that's in that disk as construction debris. Essentially, construction debris is, the hydrogen gas and any kind of minerals and materials, metals, if you will. And I'm not sure I mentioned this earlier, but when you hear me use the term metals, I'm talking about everything except hydrogen. So if I missed that earlier, forgive me. But this disk is flattening out, and this protoplanetary disk is formed. And as this disk is flattening out, it's also spinning as well, like our ice skater's skirt. And the dust that's in this disk is going to begin to stick together and form rocks and pebbles, which in turn can grow and form even larger objects called planetesimals. Over here, I kind of have a little scale to kind of show you, the relative sizes of these items. Planetesimals and planets, as they get larger and larger, gravity becomes a factor. So rather than just accreting material by virtue of spinning around in this protoplanetary disk, it's actually attracting material and using that gravitational attraction to accrete more and more material to the size of the planet in question. Beyond the frost belt, you remember this construction debris also contains gas, and this gas can coalesce and condense around dust, pebbles, rocks, probably even planetesimals to form our gas giant planets. And eventually, as these planets develop, their orbits get more defined, they'll begin to sweep away any debris that's in their orbital path. And when the new star actually begins to burn brightly in its main sequence phase, the radiation from that star will begin to blow away and sweep out any remaining gas. And that's how you're left with a solar system. And again, very simplified. There are several theories and models around this, but I just tried to summarize it as best I could here. And this is, right now we still have asteroids and other construction debris out there, but for the most part, it's not nearly as prevalent as it once was. Now, you may have heard of exoplanets. Let me grab a quick sip here. Exoplanets are planets that have been created and are orbiting other stars, and that's what exoplanets are all about. I think since the first ones were discovered in the late 80s, somewhere in the neighborhood of 5,000, maybe 5,500 exoplanets have been discovered, and exoplanets for the most part, are going to form in the same way that generally in the same way our own solar system formed. Again, that protostar, the protoplanetary disk, and the amalgamation of all that material together. So exoplanets are becoming big business. And this is just kind of a summary to show you how many exoplanets have been discovered over the course of the years. Here's an example of an exoplanet, Kepler 186f. It's orbiting Kepler 180, the star Kepler 186, and it's one of the first. I think it was the first planet discovered in the habitable zone. In other words, it could possibly support liquid water, and so I thought that was pretty interesting. And that's only about 580 some odd light years away from us, so it's relatively close to home. And that's an example of Kepler 186f, an exoplanet, again, that would have been created in much the same way as our own solar system. Okay, so we've talked about processes, and I want to use the rubric or the topic of structures to kind of take the discussion farther and discuss some objects that maybe we haven't talked about yet. So we've talked about stars and open star clusters. We talked about white dwarfs, neutron stars, and black holes. We talked about nebulas. We talked about planetary nebulas and emission nebulas. We've talked about planets and exoplanets. We really haven't touched on our own galaxy, things like globular star clusters, galaxies outside the Milky Way, and then something that's kind of maybe a new concept to unite, which are large-scale structures. So let's begin to tackle some of these items. So here's our own Milky Way, and you see circled up here in the top our own solar system. And our own solar system is roughly here out in the suburbs of the Milky Way. This is a really interesting picture, though. Maybe it's nothing new to you, but I think it for me, it really helped me kind of put everything in perspective. If you follow the view along these white lines, what you're really doing is you're looking out of the galactic plane out into, and you're looking out into the distant universe. When you're looking through in the direction of these blue arrows here, you're actually looking back into the galactic plane. And this is where you would see the stars, the interstellar clouds, the planetary nebula, all those neat objects that we find in here in our own backyard. Here is this is one of my favorite images from the presentation tonight. It shows you what I like to call our galactic neighborhood. And you can see the center of the Milky Way here. And in the middle of this circle is our own solar system. And then out this way is out towards the edge of the solar system. But let's blow this up a little bit, because this really kind of opened my eyes about a lot. So here's our solar system, and you can begin this radius of this circle is about 2 light years. So you're looking at about 4 light years from side to side. But here you can see the Pleiades, the star cluster we talked about last month, the Horsehead Nebula. We talked about the Eagle Nebula up over this way. I think the Ring Nebula is over here. Remember, we talked about the Crab Nebula, the Rosette, and the Eskimo. This really kind of is a great picture. It shows you how all these really cool objects are really in our own little galactic neighborhood. And in addition to showing us where they are with relation to our solar system, it kind of gives you an idea of where they are in relation to each other. So the Crab Nebula being in Taurus, the Rosette Nebula being in Monoceros, the Eskimo Nebula being in Gemini. You can kind of see how those 3 would kind of line up, because those constellations are kind of at similar patches, similar locations in the sky. But again, this really personally opened my eyes up about where we were at with respect to a lot of the objects that we view out in the sky. If you look at a profile of the Milky Way, you see a number of different objects here. and I'll cover some of these later on when we talk about large structures. But I wanted to just briefly mention globular clusters. Globular clusters are very cool items. But they're kind of mysterious. And I'm going to just give you a quick, brief overview on them tonight. But I've got a presentation lined up later in the year. I think it's in September by Justin McCollum, and he's going to give us a deep dive into globular clusters. So just a quick, brief discussion about them tonight. They're a spherical collection of stars bound by gravity, so similar in nature to their open cluster cousins, but they contain anywhere from tens of thousands to many millions of stars. So they are much more voluminous in terms of the number of stars in their cluster. These stars are older and denser and composed of lower abundances of heavy elements that open star clusters. So that's kind of an intriguing question, and something that Justin can probably give us much more do the topic much more do it much more justice down the road. Pardon the pun. But anyway, just a little bit about open clusters. So let's move on to galaxies. What are galaxies? So galaxies are a collection of stars, gas, dust, and dark matter held together by gravity. Unfortunately, I'm not going to delve into really much of any process behind their formation. Probably too broad of a topic for the time we have here tonight. I really need to come back to this, or line up a speaker, even better yet, line up a speaker to talk about galaxy creation and have them present. But suffice it to say, they're collections of stars, gas, dust, and dark matter held together by gravity. They probably follow a somewhat similar pattern in terms of coming together, like as say the formation of a star, but other than the gravitational collapse, that's probably where the similarities end, because they don't go on to do any of the things that star creation is all about. They are the basic element of the universe at a large scale. So if you think about a star being kind of the basic element at a small scale, galaxies are the basic element of a large scale. Most contain a supermassive black hole, and there are generally three types of galaxies. There are elliptical, spiral, and irregular. And the composition and appearance of galaxies are shaped over billions of years by their interactions with other galaxies. And we'll look at a couple of examples of that, because it's very dramatic effect. This picture right here shows you the various types of galaxies. So an elliptical galaxy is what you see up here on the top. There's very little gas and dust in these galaxies. They're filled with old red stars, and there's no rotation of this galaxy. The stars have random orbits in multiple planes, so they're somewhat kind of an unorganized mess. Spirals, on the other hand, they have a pretty good collection of both old and new stars, and they do rotate. And the agitation of the turbulence stirred up by that rotation is probably responsible for creating or promoting star creation. And then these irregular galaxies that you see down here, these they have an ill-defined shape. There's no spiral arms or central bulge. However, they may contain hot gas and dust, or a lot of gas and dust rather, and can be active star creators. Now, Hubble had come up with a tuning fork diagram, which he used to catalog different types of galaxies, similar to what you see on this diagram here. He incorrectly thought of it as an evolutionary sequence. In other words, that an elliptical would eventually form into a spiral galaxy, and that scheme was not accurate. Galaxies can change, but they can change. They typically will change through their interactions with other galaxies. So, but it was a good starting point. for cataloging galaxies. So here's a couple of interactions that I want to walk through that kind of show you how galaxies can work together, either work together or destroy each other, depending on how you look at it. Here's a picture of M81 over here and a starburst galaxy called M82. And M82 is undergoing an exceptionally high rate of star formation in comparison to the average galaxy. And if you look closely here in the center, you can kind of see a red crease. And that red crease is the starburst activity that's going on. And it's thought that this close encounter and subsequent gravitational effect from M81 is the driver for this starburst activity. These galaxies are about 130,000 light years apart. This baby here is about 38,000 light years in diameter. This M81 is about 74,000 light years in diameter. So relative to their size, this distance isn't very, very big. And when you get two objects of this size, even being that far apart, they can have a profound effect on each other. A more dramatic example of a galaxy interaction is this picture here of M51 and NGC 5195. So it's thought that these two galaxies actually collided about 500 or 600 million years ago. And currently, this galaxy over here, due to the gravitational effect on M51, is helping to give the spiral arms in M51 this very pronounced and circular look. So again, another example of two galaxies coming together and fundamentally changing each other's contours and size. You've seen pictures of the antenna galaxy. That's probably the most dramatic example of two galaxies coming together and interacting with each other. But these are two examples that I could pull together for this talk that I thought illustrated the point pretty well. So I've mentioned earlier that galaxies are the fundamental building blocks of the universe at a large scale. Galaxies can actually come together and form groups and clusters, and then groups and clusters can come together to form what they call superclusters. So a group is 50 or fewer gravitationally bound galaxies, and we are in a group called the local group. And I'll show you a picture of that here in a second. Clusters, on the other hand, are much larger. They are 50 to 1,000 gravitationally bound galaxies together. And then a supercluster is a large group of clusters and groups. Superclusters they're not gravitationally bound, but rather they expand because of their large size and low density. And there are about 10 million superclusters estimated to lie in the observable universe. So a lot to wrap your head around here. Maybe a picture will help kind of get you oriented on this. So here's a picture of the local group. This is where the Milky Way belongs. This picture here is about 6.5 million light years in size. Here's our Milky Way in yellow, which means that we are a big, full-fledged spiral galaxy. Over here, you see Andromeda and Triangulum. Again, two large, fully developed spiral galaxies. And then the rest of these galaxies that you see here in blue type are dwarf galaxies or regular galaxies. I hate to use the term minor, but in comparison to the Milky Way and Andromeda and Triangulum, these are minor galaxies. But this is about what our local group looks like. Our local supercluster, and again, there are groups and clusters, and we're in a group, and our group belongs along with 3 other clusters in a thing called a supercluster. And this is, again, a collection of groups and clusters. Here's our local group right here. The Virgo clusters over here. We talked about M81 and M82. They belong in this M81 group over here, and so on and so forth. Now, when you get to this point in looking at structures, it gets a little bit esoteric, and and I apologize for that, but at some point you got to kind of get acquainted with this. This area of space is about 195 million light years in size. And if you look at our own supercluster, here we are in the Virgo supercluster in relation to a bunch of other superclusters. You'll notice too here on this picture, stuff called in this red type called a void, and this other nomenclature called a wall. These are even super large structures. I was going to try to talk about these tonight, but I think this is as far as we'll take it tonight because it really got complicated and probably wouldn't fit in an hour of our time. So that is our nearby superclusters that are our neighbors in the universe. And that's a lot to wrap your head around. So I wanted to kind of end our discussion of structures with this series of slides here to kind of help you get your feet landed on where we are in terms of our own galaxy and everything else. So here's Earth, and we are the third rock out from the sun in our solar system. Our solar system is smack dab in the middle of this 4 light year area called galactic neighborhood. And our galactic neighborhood is out here in the suburbs of the Milky Way. We're about halfway between the center of the Milky Way and the edge of the Milky Way. Our Milky Way is located in the local group. Our local group is located in the Virgo supercluster. And the Virgo supercluster is out here amongst a number of other local superclusters. And this is a little artwork on my own here, but this is just a notional picture to kind of show you how much space, even at the local supercluster size, we inhabit of the observable universe. So that kind of gives you a quick thumbnail sketch to understand where we fit in the world out there. I want to kind of make it real, though, before we wrap up the presentation tonight. And I get the biggest kick out of this picture. As Joe mentioned, I volunteer at the George, and over in the East Dome, we were showing the Ring Nebula one night. And the Ring Nebula is very close by. It's only about 1,400 light years away, and it lies well within our own galactic neighborhood. Well, Jeff Lepp was out with us that one night, and he pointed out over here a barred spiral or a spiral galaxy, IC 1296. And as it turns out, this galaxy is 260 million light years away from Earth, which means if I did my math right, it lies beyond the Virgo supercluster. And the cool thing about this whole thing is that it wasn't a bunch of top-notch MIT researchers that were able to bring this to the public, but really 3 amateur astronomers. Granted, we had access to an 18-inch reflector telescope, but 3 amateurs were able to find this galaxy, put it up on the screen, and share it with the public. And I just think that's such a cool thing. Hopefully brings out that whole esoteric discussion about groups and clusters home with you a little bit. Okay, so let's just kind of wrap up here. Let's see how we did on our 3 questions. We talked about how stars are formed from stellar clouds or nebula via gravity and fusion. Stars of similar age and composition can form open clusters. We talked about how construction debris from star formation formed our planets and can form exoplanets. When small stars die, they form planetary nebulas and white dwarfs. When large stars die, they form supernovas and can form either a neutron star or a black hole. The remnants of stars enrich the cosmos with metals. Gas, dust, and dark matter can come together and form galaxies. And again, I owe you more on galaxy formation. This was just a kind of a starting point. Galaxies can interact with each other and affect their structure and star forming rates. Many familiar objects are located in and around our galactic neighborhood. Galaxies can aggregate into groups, clusters, and superclusters. And then in this last series of slides, we traveled from Earth to the Virgo supercluster and beyond. So I think we did a fair job of answering those questions. I want to leave you with these three resources. The first one is called The Evolving Universe. It's a course offered by Caltech through Coursera, and the instructor is Professor George Observatory. The second course is Exploring Time and Space. It's offered by the University of Arizona, and it's taught by Professor Chris Empey. And there's a universe guidebook, The Celestial Zoo, that's author Pablo Carlos Budassi. This is a great reference. It really talks about structures more than anything else. And it's a wonderful resource, and I highly recommend it. And I also want to give special thanks to George, Chris, and to Pablo. When I reached out to them for permission to use course material and images from the Celestial Zoo, they not only gave me permission for to use the items I requested, but opened up their whole library. So I really appreciate that, and I couldn't have done it without them. And with that, I thank you, and I will open it up, give it back to you, Joe, and answer any questions if I can.
Yeah, I appreciate that. That was a fantastic talk, Chris. Learned a lot, and I've always been fascinated by these views of where we are in the universe. And you've probably seen the Powers of 10 presentations online and things like that really kind of start off with us and then take a factor of 10 view outside of that and then continue to grow that beyond. It's always fascinating, and it's always, to me, mind-blowing to think that when we look outside and we're looking at the stars in the night sky, most of what we see is really in our own backyard,
right.
Figure of speech. But many of these objects are well within 100 light years. Some are a few hundred light years and things like that. And then obviously, once we train our telescopes on the skies, we're seeing well beyond that. But even then, we're only seeing a tiny portion of the universe around us. So I thank you very much for the presentation. It was absolutely fantastic. So with that, I will ask anybody who wants to ask a question to come off of mute and ask away. We didn't have anything in the chat. I think everybody was kind of fixated on what you were talking about there, Chris.
Hi, this is Cora. Can you hear me?
Hi, Cora. We can hear you. Yes.
Yeah. So my quick question, Chris, and I may have missed it, but why do some stars form planets? But I'm assuming, since we haven't found that many exoplanets, at least just yet, that there are stars that don't form planets.
Yeah, I mean, it's a great question. I would hazard to guess that the level of metals in the in their construction debris is not sufficient to create planets, or just by the very nature of its development, particularly with a large star, the star may be so powerful that it just blows that protoplanetary disk away if any disk ever formed to begin with. That's just my own thought on that. And you reminded me of one thing in the Board of Visitors last winter's meeting. They talked about their quest to find exoplanets, and they're focusing in on the smaller planets. And if I remember the discussion right, it was because they don't have they don't have that violent expulsion of radiation that would destroy any material around it. And I think the other reason too is these smaller stars can support larger planets, which we can detect more easily. But anyway, that's my educated guess on that, Cora. I don't know if that answered your question or not, but
it does. Thank you. That does, and it makes sense.
Cora, I'm going to go ahead and paste a presentation that we had last year. I think it was May. We had Dr. Christopher Johns Kroll, who's a professor at Rice University. He actually talked about the whole field of study that they're doing around exosolar planetary system creation and things like that. I think that might help expand on some of the questions that you have there. So let me go ahead and paste that in the chat here, and anybody else you wish, to feel free to watch that as well.
Great, thanks.
Certainly. All right. Any other questions for Chris? Hey, Chris, I think you gave us a lot to digest. I'll give everybody else another minute or so to see if they want to come off of mute and ask. Like I said, that was an absolutely fantastic presentation, Chris. Thank you.
You're welcome.
For anybody who might have questions, I did want to mention, you might have seen the post on the HAS website or the Facebook page yesterday. Very well-renowned astronomy author, Terrence Dickinson. I'm holding up a book by Terrence right now. This is Night Watch. You may have also seen the Backyard Astronomer's Guide. Terrence passed away yesterday, or I believe the day before. And I can't say enough about how much he influenced not only my journey in amateur astronomy, but I'm sure the journey of many, many countless others with his books. These are two of the more popular ones, but you talk to anybody who's been in astronomy for a while, and when they're telling people who are just getting into the hobby where to start, most often they reference Terrence's books. So, certainly a loss to the amateur astronomy community. And, we're fortunate we've had the opportunity to get the books and all of the knowledge he shared with the rest of the community, but that is a huge loss here. So just wanted to pass that along for those of you who had not heard, and, just share that news. So any other questions for Chris before we wrap up tonight? All right. Well, Chris, if you wouldn't mind, I will, if you wouldn't mind removing or taking the share off, I'll share.
Yep.
Thank you. Desktop 3. All right. Again, Chris, thank you very much. That was an absolutely fantastic talk. We do have a presentation tomorrow. Our February general meeting will be tomorrow evening at 7 p.m. Please be sure to join us then. We have Dr. Neve Grory from the University of Texas and McDonald Observatory, who's going to be talking about cosmology. So kind of taking your theme, Chris, here and explaining what it is that they're doing at the McDonald Observatory and some of the things that they're understanding about the creation and development and further evolution of our universe and our cosmos. So please be sure to get registered there if you have not yet. The registration links are on our website, astronomyhouston.org. And as usual, I always kind of wrap these things up by saying, if you're on any of the social media platforms that we have listed here, please give us a follow. I put a link in the chat to one of our video presentations from several months ago. You can see many of those that are on our YouTube page. So feel free to follow us at any of those. And if you have any questions, by all means, send us an email at info@astronomyhouston.org. So, Chris, again, thank you very much. Fantastic talk. We'll go ahead and get this buttoned up and put on the YouTube site as well, so others can rewatch it or watch it if they haven't had a chance to do so yet. And we'll get that out to everybody in the next few days. Otherwise, we hope to see you with us tomorrow night. And if you don't join us tomorrow night, hopefully you can join us for one of the events that we have planned for next week. Thank you very much, everybody. Have a great evening. We'll talk to you soon.
Thank you, Joe.